Welcome everyone. This talk is about the reconfiguration of basis pairs in regular Matroids, and this is a joint work with Bence Matroids, who is a master student at ETH, and with Tamás Schwarz, who is a PhD student finishing this year at the Atoshi University. If you are listening to this talk, then most probably you are familiar with the notion of Matroids, but let me quickly recall the basics. So, a matroid is defined by a pair E and B, where E is a finite ground set, and B is a family of subsets of E whose members are called bases, satisfying the so-called basis axioms that you can see here. From those, we will use the second one, which is often referred to as the symmetric basis exchange axiom, saying that given two bases, B1 and B2, and an element in B1 minus B2, one can always find another element in B2 minus B1, such that exchanging these two elements results in two bases again. Then, by an independent set, we mean a subset of bases of M, and you could also define matroids using the independent sets, but now we stick to the basis axiom. Okay, so basic examples for matroids include linear matroids, whose ground set is a set of vectors over some field, and bases are exactly the subsets of vectors that form bases in the linear algebraic sense. Another fundamental example is the graphic matroid of an undirected graph, whose bases are the spanning trees. And if you are familiar with the notion of duality in matroids, then the dual of the graphic matroid of a graph is called the cographic matroid, and in the cographic matroid, the bases are the complements of spanning trees. But in this talk, we will concentrate on regular matroids. So what's the definition of regular matroid? A matroid is called regular if it is linear over any field. That is, if it can be represented as a set of vectors over any field. And the nice thing about regular matroids is that we have a very good understanding of their structure due to a result by Seymour, namely the following. So Seymour's decomposition theorem states that every regular matroid can be obtained using only three types of building blocks, namely graphic matroids, cographic matroids, and the fixed matroid, which is called R10. I will show you the definition soon, using certain matroid operations that are called 1, 2, and 3 sums. Okay, so what are these operations? Let me give a definition for graphs first. So if you're given two graphs, G1 and G2, then for an integer k, the k sum of these two graphs is defined by taking a k click in both graphs, identifying the vertices of these k clicks, and deleting the edges of the click itself. Okay, so here on these figures, you can see an example for a 1 sum, a 2 sum, and for a 3 sum of two graphs. And it turns out that these operations can be extended to matroids as well. I will not go into the details here. Okay, and what is a matroid R10? So this is a matroid that can be represented by this matrix that you can see here. Think of the elements of the ground set as the columns of this matrix, and independence is then defined as being independent over the two-element field. Okay, so we consider some elements of the ground set to be independent if they are independent over the two-element field. Okay, so after this short introduction, let me specify the problem that we are interested in. Let A1 and A2 be a pair of disjoint bases of a matroid. Then, according to the symmetric exchange axiom, one can exchange elements between these two bases such that we obtain another ordered pair of bases. So here, on this example, we start with a graphic matroid. The two colors denote two spanning trees, so those are two bases that are disjoint. And doing a symmetric exchange, we can construct two other bases of the matroid. And then you can repeat this step. So that means the following: if you start from any pair, then you can reach many others by sequences of symmetric exchanges. And this raises the following problem. Let's say that we are given two pairs of disjoint bases, A1, A2, and B1, B2. And the question is, when can we reach one from the other by a sequence of symmetric exchanges? And this problem was posed by White in 1980, and White conjectured that such a sequence always exists if the union of the bases in the starting and in the target pairs are the same. Okay, so this is clearly a necessary condition because while we are doing the exchanges, the set of elements covered by the union of the two bases will not change. So this is clearly a necessary condition. But White's conjecture states that if this condition is satisfied, then we can always reach one pair of bases from the other one by doing symmetric exchanges. Note that this conjecture says nothing about the length of the sequence or the number of exchanges needed to transform one pair into the other. And a few years earlier, actually, Gabo studied a related problem and conjectured that when the starting and the target pairs are related, namely only the order of the bases is changed, so we want to go from the pair A1, A2 to the pair A2, A1, then one can always find a sequence of rank at most the rank of the matroid. The rank is denoted by R. Okay, so these are two separate conjectures. And let me also advertise a third one, which is not so well known, but I think it's a really nice question, and it's also closely related to both of these conjectures. This conjecture is called the equitability conjecture. The conjecture states that if the ground set of a matroid is the union of two bases, and X is an arbitrary subset of the ground set, then the ground set can be partitioned into two bases in such a way that the two parts contains almost the same number of elements from this set. Okay, so on this figure, the first figure, you can see a decomposition into two bases, and the yellow elements are the members inside X. And on the second figure, you can see a decomposition into two bases that contain the same number of yellow elements. Okay, and the conjecture says that if the ground set of the matroid decomposes into two bases, then no matter how you choose X, you can always find the decomposition into two bases where the two bases share almost the same number of elements with X. And it is not difficult to see that both White's and Gabo's conjectures would imply the equitability conjecture. Okay. So though these questions might seem to be rather theoretic, actually these are related to many problems in mathematics, such as fair allocations of indivisible items or reconfiguration problems on matroids. I will not explain the details of the connections here. However, the probably most interesting connection is to sampling. So in sampling, the goal is to, for example, if you're given a matroid, then you can ask the following problem, give an algorithm which gives you a random basis of the matroid. And there are fundamental recent results related to sampling, and the sampling techniques usually relies on the so-called down-up random walk. Such a walk is defined using the basis exchange axiom. And the problem is that there is no similar result for the intersection of two matroids, since the exchange axiom does not extend to the setting. So when you are given two matroids, then for common basis of two matroids, the symmetric exchange axiom does not hold. And the message of White's conjecture is exactly that maybe such an approach could still work for sampling a common basis in the intersection of two matroids when the two matroids are dual to each other. Okay, so these are some of the motivations of our investigations. Okay, so what do we know about these conjectures? The conjectures were verified for various matroid classes, most importantly for graphic matroids. White's conjecture was settled by Farber, Richter, and Schenck, and Gabo's conjecture was proved by Cordoville and Moreira. It is not difficult to see that if the conjecture, any of the conjectures hold for a matroid, then it also holds for the dual of the matroid. So actually these results imply that we have the same results for cographic matroids as well. Since graphic and cographic matroids are exactly the main building blocks in the decomposition of regular matroids, right? Remember Seymour's decomposition theorem. It is natural to ask if the proofs can be extended to the regular case as well. And this problem was asked already by Farber et al. And the question also appeared in a recent work by Andres and his co-authors. Okay, so that was the starting point of our investigations, and our main result is verifying all the previously mentioned conjectures for regular matroids. Okay, here you can see the precise statement. So let me emphasize that we do not only prove White's conjecture for regular matroids, but we also give a polynomial upper bound on the number of symmetric exchanges needed to transform one pair of bases into another, and our proof is algorithmic in the sense. So since we are talking about matroids, we assume that the matroids are given by an independence oracle, and if you have access to an independence oracle, then actually our proof implies an algorithm that makes a polynomial number of calls to the oracle and finds a sequence of exchanges, transforming one pair of bases into the other. And the idea of the proof is exactly what you would expect. So first, by Seymour's theorem, one can decompose the matroid into graphic, co-graphic, and R10 parts. Okay, so that's one thing that we know for sure. And then the idea is to find exchange sequences in these smaller parts. So basically, we divide the original problem into sub-problems. And we are hoping, one can hope that finally, if we find these sequences in these smaller parts, then somehow we can merge these sequences together at the end. And this indeed seems to be a very simple approach. The problem is that performing the last step, the merging step, is far from being obvious. So it's not clear how to merge these sequences in the smaller parts to obtain a correct sequence in the original problem. And in fact, it turns out that you really have to be careful in how to do that. So in the rest of the talk, let me just highlight the key ingredients of the proof. Once again, this is the high-level idea. We take a regular matroid, we consider its decomposition provided by Seymour's result, we find exchange sequences in the smaller parts, the graphic, the co-graphic, and the R10 parts, and then we merge these sequences together. That's the idea. So our proof starts with some pre-processing steps. These include showing that the bases in the pairs can be assumed to be disjoint. Actually, for simplicity, when I stated the conjectures, I stated those for pairs of disjoint bases, but originally White and also Gabo stated those conjectures for not necessarily disjoint bases. But the very first step is observing that you may assume that the bases are disjoint. And then the second observation is that you may assume that there are no tight sets in a matroid. A set is tight if its size is exactly twice its rank. And the reason why you can assume this is that if you have a tight set, then you can reduce the problem size by considering minors of your original matroid. Then we show that you can assume that the matroid has no two separation, which implies that it's not the one sum or two sum of two smaller matroids. Again, if it's the one sum of two or two sum of two smaller matroids, then you can apply induction. And then this is not so obvious why this is interesting, but you can show, and this is a technical proof, you can show that the matroid has no cocircuit of size 3. Okay, so these are all small technical lemmas, but the main takeaway from those is that the matroid can be assumed to be free connected and containing no triangles. Okay, so this is the main takeaway from these observations. Okay, so now we have a matroid which is free connected. So if you consider Seymour's decomposition, then only 3 sums are used in this decomposition. And actually, we need to use a refined version of Seymour's decomposition theorem, which is due to April and Fiorini. And I do not want to go into the details here, but the main point is that if you combine this refined version of Seymour's decomposition theorem, so the observation of April and Fiorini, you take an observation of McGuinness, and some technical lemma on the dual of a matroid obtained from a co-graphic matroid by some matroid operation that is called a Y delta operation, we can identify a graphic matroid sitting at the end of the decomposition, meaning that, so basically that's the main thing here. So we arrive to the conclusion that we can assume that the matroid can be written as the 3 sum of a regular matroid, which is smaller than the original matroid, and a graphic matroid, which we denote by M2. So all these observations are needed to conclude that we have this graphic part which is separated in the decomposition. Okay, and now we are almost ready to apply induction by saying that, okay, we have a smaller regular matroid M1 and the graphic matroid M2. So the idea is to find a sequence for the graphic part and apply induction for the regular part and merge those sequences together. However, there are 2 difficulties here. First, we do not only want to show the existence of a proper exchange sequence, but we also want to provide an upper bound on the length of this sequence. And without carefully choosing the sequences in the smaller parts, the number of exchanges step can blow up. And the other problem is that merging the sequences, whatever that means, so I will not, these are really little technical details that makes the proof somewhat complicated, but what I want to emphasize is that merging these sequences is not always possible. So the sequences in these two parts, so in M1 and M2, must be chosen carefully. And to overcome these difficulties, we actually prove a stiffening of White's and Gabor's conjecture for the graphic case. So here, the key ingredient at this stage is that we have some stronger statement in both cases, and having this stronger statement enables us to apply to prove something stronger in the inductive step. Okay, and finally, after all the reduction steps that we had so far, we analyze the structure of the graph corresponding to M2, and also verify the conjectures for this matroid R10, and also for the final matroid. So F7 here denotes the final matroid. I will tell you later why the final matroid is interesting, but verifying the conjectures for the final matroid is just a small additional step. And after all these, we are able to provide that a polynomial upper bound and a number of exchange steps for regular matroids, which in turn verifies the statement. So this is a bit more detailed description of the proof, but it's still, as you can see, it involves a lot of technical details that needs to be put together to get the proof at the very end. Okay, so summing up, we proved all three of the conjectures that I mentioned in the beginning of the talk, and in fact, our results extend to the class of max flow mean cut matroids. So MFMC matroids MFMC matroid means max flow mean cut matroid, and we needed the observation for the final matroid for this step. So actually, we almost get this result for free once we know that the conjecture is also hold for final matroids. The details are in the paper. And there are several open problems remaining. Let me just mention two of those. So actually, White formulated his conjecture in a stronger form. He formulated his conjecture for basis sequences instead of pairs of bases. And this more general version is also open, of course. But it was verified for graphic matroids. However, for graphic matroids, it's open whether we can bound the number of exchange steps by a polynomial of the rank. Okay, so for basis pairs, we have seen that actually we verify that rank square many steps are enough for transforming one pair of bases into the other. But for longer sequences, it's open whether you can provide a similar upper bound. And another interesting problem is Amidou's conjecture, which states that for any pair of bases, so if you have, if you have any pairs of basis pairs, so A1, A2, and B1, B2, then you can always find a sequence of symmetric exchanges of length at most the rank that transforms the first pair into the other. Okay, so Amidou's conjecture is somehow a mixture of White's conjecture and Gabor's conjecture, because it says that, all right, we can go from one pair of bases into another by using symmetric exchanges, and even more, we can do this in a small number of steps, actually linear in the rank. And so in this context, this conjecture provides a common generalization of the conjectures of White and Gabor. Okay, that's all that I wanted to say. Thanks for your attention. If you are interested, I'm very happy to discuss these problems with you. Here you can see my email address and the webpage of the research group.